we want to look at carbocations. Right? So carbocations are a carbon with only 6 electrons. Right? So this is going to be really important that it's only got 6 electrons, which means its valence shell isn't filled, right? So typically a carbon wants 8 electrons, but if it only has 6, it's got a spot for 2 more. And it typically has a positive charge, right? So it's got 6 electrons and it then has a positive charge. All right, we're going to be able to classify that carbocation as a primary, secondary, or tertiary. And the way we're going to do that is we just want to look at the carbon, right? So if it's a carbon with 3 hydrogens, right, so let's look at this one. There's a carbon here with 3 hydrogens, and it's attached to another carbon. This carbon only has 3 bonds, 1, 2, 3. So that means it's 6 electrons and then a carbocation. Both of these carbons, since they're only attached to one other carbon, are primaries. Okay? And so that's why that would be on a primary carbon. Let's try one in the zigzag form. So if you go through, if we had a carbocation here, this one is on the end. So this would be a primary carbocation. Okay. Take a second and try to identify the degree of the carbon for the other 3 that I've indicated with the arrows. All right, and that's going to be that same degree that you find them will be the same degree that it would be if it was a carbocation. So go ahead and pause the video and give it a try. All right, so how did everyone do? So this would be a secondary because it's attached to a carbon on the left and a carbon on the right. The one in the middle would be a tertiary because it's attached to a carbon 1, 2, 3. And then the one on the end would be a primary because it's only directly bound to one carbon. All right? And one of the things we're going to talk about here in a minute is the more substituted, the better. All right, and so I'm going to put the better ones on this side. So if you have to pick, the tertiary carbocation is the most stable, and then secondary, and then primary, and then a methyl would be the worst. All right. They're really, really good electrophiles. So remember, electrophiles are anything that wants electrons. We're going to associate positive charges with electrophiles. So anything that can accept electrons can be a good electrophile. Carbon wants 8 electrons. So it's going to be really looking to fill that empty valence shell. All right. There are Lewis acids, because remember, Lewis acids are electrons acceptors. When we talk about stereochemistry, this is going to be really important that if it's only got 6 electrons around it, that means it's only got 3 groups. This carbocation sits in an empty p orbital. And that means the bond angle around these 3 groups is going to be 120. Right? And it's because you're going to have an unhybridized p orbital, so down here at the bottom, which lies perpendicular. So essentially, if we have our carbon, we're going to have our empty p orbital going up and down. And then, let's say we had hydrogens just to make the picture look easy. Those would all sit in the same plane. All right, so those would all sit in the same plane. And then perpendicular to that would be that empty p orbital going up and above. So you can almost assume that that p orbital would be going up and down like this Apple pencil, right? Going up and down from the plane. And then the hydrogens or whatever carbon groups would be even with my hand. And so it makes it completely flat. And then we can spread the 3 groups out with 120 bond angle. And so here's exactly what we're talking about. We have those different groups, right? So here's our 3 groups. And this is supposed to show like a sheet of glass, right? Showing they're all in the same plane. And then here's my empty p orbital. So when we have electrons, they can push into this p orbital. Bond angle is 120, right? And that's because we're spreading these groups out as far as we can, right? So generally that's VSEPR, right? Oh, sorry, excuse me. So we're going to spread these groups out as far as possible. All right. This one, I would make sure that you commit to memory. The more substituted that carbocation is, the more stable. Right? Meaning this is a tertiary. And so we really want to highlight these numbers here on the bottom. And then a methyl is when it's just 3 hydrogens. And so the more substituted, we're looking at this carbon, The more groups it's attached to, the more stable it is. Okay. Down here, there's a statement. Methyl and primary are really unstable, so they really don't form very well. All right, so every now and then they'll form for just a moment under certain conditions, but for the most part, they don't really form very well. When we get to the tertiary, it happens a lot better. Same thing with secondary. We're going to come back to this idea when we look at reactions, and specifically when we talk about mechanisms, because one of the intermediates we're going to see for some of our reactions are these carbocations. And so we want to really examine what makes the most stable carbocation. Now, we just talked about that the tertiary carbons are the most stable, right? And so the tertiary, and I'm just going to draw it out just to make it a little bit easier to see. So if we have a carbon here, actually, let me get a better color. I think that might be hard to see. We have our carbon and then a CH3 group, and another CH3 group. And we're going to have this empty p orbital. What the inductive effect says is that we can push some of the electron density from each of these carbons. And that's what this picture here is trying to show you, is that there's a little bit of electron density from each one of these carbons that we can contribute in. Every time we have a carbon, there's some electron density we can push in. If it's a hydrogen, there's nothing to contribute, right? So there's no electron density we can contribute. And so that's the problem why a methyl is so unstable, is there's nothing helps stabilizing that positive charge. And so induction isn't like resonance where we can formally move the electrons, but we can push a little bit of electron density. Right? And so that's what this is talking about. Is we're trying to help that positive charge a little bit by sharing a little bit of our electrons towards that way. Right? So we don't formally move them, but we push some of that electron density. Right? And that only works if we have a carbon group, not if we have a hydrogen. One more idea is hyperconjugation. So if you remember, we are going to have our empty p orbital. Right? So everyone can see this one here with the pink and blue. And then over here is our carbon with a CH bond. This is my hybridized orbital, but they almost line up like goalposts. Right? And so the reason that's important is when they're in the same plane, right? They line up just like a goalpost would. You can actually share electron density from that hybridized orbital into that empty p orbital. So we could push a little electron density into it. And so that helps start stabilizing that carbocation. The problem, if it's just a hydrogen, so you can see the hydrogens here on the left, and let me highlight those in orange, is that they're going straight out. So there's nothing going to line up in that same goalpost configuration that can help. Now, the thing that would happen is the more substituted this group becomes, so if we have a CH3 over here, I'll put the other two hydrogens, and then a carbon with another hydrogen, and we have our empty p orbital, what we can start to get is sharing of electrons from here. Right? And then we can get some sharing of electrons from the other one. And so you can see the more carbon groups we have off of that central carbon with the carbocation, the more groups it can contribute in. Right? Now you can see if we add a third group, we can contribute again. And so we can constantly keep contributing into those orbitals, right? And so we line them up and we share that electron density. So again, this is just highlighting why that tertiary carbocation is the most stable.